Yeah. Happy morning, Shubham Munjani friends. We lost two sessions, potential and potential energy was our topic. Given good number of results, hope you are ready with them. Today's session, we will do some simple examples on potential and also potential energy. First example I said, point charge, some positive charge 3 microcoulomb placed at this position 2 minus 3 4 given in SI units. This is the position of our capital Q, the charge. Now he says find the work done in moving another charge. That second charge is given to be minus 5 nanocoulomb, a negative charge is given. Multiples is also very important. Some multiple here it is micro, this is nano. Good observations. And now this is moved from the point P. The location is 3 minus 2 1 to the another point. So I call it Q. To another point Q, which is 4 minus 4 1 3 meter. Q, if I have used it earlier, let me use this point as some R. This is the position minus 4 1 3 meter, and we need to find the work done. Remember, when you are dealing with examples, always it is important about the keywords. Here, the charges and displacement from between two positions and the work, what is our fundamental should be your take. The first, let me write the data. Data says that Q, the capital charge, is 3 microcoulomb. 3 microcoulomb is the fixed charge. The fixed charge, and the moving charge is small q. I write it as minus 5 into 10 raised minus 9 coulomb. This submultiple is an important thing. Now the displacement is from P to R. Is it not? Now I am writing, since displacement of small q is from P to R. Now what I do is that I will consider this OP is equal to R1. OP is equal to R1, which will give you the distance between two positions. Very familiar, popular result. Root of x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. So accordingly, where it is moved from O, and this is P I am taking, so OP will give you, this is under root 3 minus 1 whole square, then 2 minus of minus 3, right? So plus 2 minus of minus 3 whole square plus Z2 minus Z1 whole square. This is minus 1 minus 4. So this is minus 1 minus 4 whole square. This becomes R1. So this, of course, you write it. This one R1 is equal to, this is 4, and this is this becomes 5 is equal. Yeah, 5 square 25, and this is also minus 5 square. This is 25, 25, and 4. 25, 25 and 4 is under root 54 meter. Is that okay? So one more time, you please look at this simplifications or calculations. In fact, it should be your part, but still this is 2 minus of minus 3 plus 5 whole square, and this is minus minus 4, 25. So this is under root 54, under root 54 meter. Similarly, now you can write R2, R2. This is what is OQ. OQ is equal to R2. See why we are actually doing this. This is what is OP and OQ, because now we are writing potentials at two different points, and that is what is our job. So to write potentials, we need distances. That's what I am doing. We can also do it in another way, taking the displacement vector and all. So this is one fundamental way I am just showing you. And similarly, what is that OQ is given by? This is under root. Yes, this is minus 4 of minus 2 minus 4 minus 2 squared plus 1 minus of minus 3 plus 3 squared and plus z2 minus z13 minus 4 squared, which will be around, so this is 36, right? This is 36, this is 16, right? Therefore it is 52 and 52 plus 1, it is 55. This is 55. That number. Supposing if I want to change, let me take number as some 5, this one is 5, then this is, okay, let me take this as some 7, because for bigger numbers, 7 minus 4 squared, therefore it will be, this is 36 and 16, 52 and then 9, right, 61, under root 61 meter. Now, what we need to do is that work done. What is the definition of work done? Now, first we will write V at P is equal to 1 by 4 pi epsilon naught. The potential is due to which charge? The fixed charge, which is 3 microcoulomb. Therefore, this is 3 micro, and what is the distance? It is under root 54. This is what is Vp value, and this will be around, this is 9 into 10 raised 9, this is 3 into 10 raised minus 6, and what is that? Root 54. That value you need to write, I don't do that. Under root 54, how much we'll get? So if it is 49 under root, it will be 7, and it is root 64, you will get 8. This is something around root 54. The number you will choose from 7.4, 7.6, whatever number that you get, that you will do. Again, I am telling you here, I am doing a small estimation approximation, otherwise you do it on your own. This is something I will write as some 7.5, supposing if I write 7.5, supposing if I approximate I am doing, please remember this is what is comes around 27 by 7.5, right? 27 by 7.5, and this is 10 cube, and this is what is volt. Similarly, what is V cube? V cube is equal to, again, K cube by R relation you will do. K cube by R relation you will do. This will be again 1 by 4 pi epsilon naught, 3 into 10 raised minus 6 under root 61. So this will be again 9 into 10 raised 9, 3 into 10 raised minus 6 upon this under root 61 again. Root 64 will give you 8, and therefore root 61. Some number I am writing, I am not sure about any of these things. Completely this is your job. Supposing if I am doing it as some 7.8, suppose I am doing 7.8 I am doing. Then this will come around again. This is 27 by 7.8 times 10 raised 3. Those kilojoules, it will be the answer, right? So this is 27 upon 7.8 into 10 raised 3, and in the units of volts. So we have what calculated is potential at P and potential at Q. Potential at P and potential at Q. Now what is to be done is calculation of work using our fundamental definition. What is that? W equal to potential difference times Q. So our definition is, remember, the work done, electrostatics, the key word is charges, displacement and the work. So I will give you that statement, and the simplification and further answer, you please do it on your own. Therefore now, W, and I have told you always whenever you are calculating, the signs are important, the charges are important, the sign given to the charges are important. Therefore now here you are going from P to R. Therefore this is P to R equal to VR minus VP times Q. VR minus VP times Q. So this is actually our definition. Order is important, P to R. Then this is initial point, P final point, or here final minus initial time, this Q, and this Q to be taken along with the sign which is minus 5. Therefore, here is R, is it not? Yeah, whatever that point, V equal to R. So what did you observe? Here in this case, VR is less than VP. Is it not? VR less than VP, and therefore here VR minus VP will be a negative quantity, and negative quantity multiplied with it, and therefore the final answer that you get will be in the positive numbers. Is it not? Don't forget about these numbers. Whenever you are calculating the work or potentials or potential energy, the sign given to the charges are very, very important. This is of course a positive charge, and the mobile charge is negative charge. Hope you got the answer right. Do the calculation, get your answer. See, in the earlier example, when the moving charge, we said displacement, positions were given as P and R, or the position of the fixed charge is given in terms of coordinates, is it not? Now here, the same question, no difference whatsoever. In fact, it is much easier because we have distances that can be done very easily. In such, but a small change, because now here I have shown a figure. Number of times I have told you earlier also in the classroom that whenever figures are given, the student takes it as a very difficult question. Nothing difficult. In fact, whenever a figure is given, our job is half done, because looking to the figure, we can get the solution. Now here I said ABCD is a square. It is a square. Supposing I said a square of side 1 meter. ABCD is a square of side 1 meter. Such that a point charge of minus 5 microcoulomb is placed at the vertex B. It is a fixed charge. And work done, you are asked to find work done in moving another point charge of plus 2 microcoulomb. This charge at where we have placed at B is capital Q, supposing, and if I consider this as some another charge, Q1, Q2, capital Q, small q, whatever symbols, this is another positive charge. Now he has said, find the work done in moving from A to D, D to A, any such displacement is given. Now here I asked for the 3, from A to D, from D to C, from A to C. Now remember, of course, when I am doing this, you always know that it is a work done in the case of electric field, conservative field, therefore it is independent of the path. Supposing if I say A to D, if it is straight line path or any curved path, it doesn't matter. It depends only on initial position and final position. Therefore, here also, when I take up this first case, capital Q is equal to, yes, it is a negative charge of minus 5 microcoulomb, that is given minus 5 into 10 by minus 6. And therefore now I will simply calculate what is V at D and what is V at A. Because displacement, charges and work done, nothing but potential difference times the charge which is displaced. So to find the potential difference, now we have two positions, D and A. Therefore here it is K, capital Q, by, what is that D? From B is nothing but the diagonal, is it not? Since AB is the side, the diagonal becomes root 2 times, therefore the answer is KQ by root 2 volts. KQ by root 2 volts, and what is VB? K capital Q by A is a distance of 1 meter, therefore I will write it as 1. So it is KQ by root 2 and this is KQ by 1. What does it mean? It means that, please look here, at B whatever charge we have placed is negative charge. Negative charge, and the magnitude wise talking, this is this value is KQ by root 2, which is lesser in number, this is more in number. So immediately, since it is a negative charge and negative potential you are talking about, immediately what you will make out is, now this VD greater than VA is an important pick that you have to make. Remember, here these are the negative values. Negative values that you will consider, or else if I want to show you, this is what is 9 into 10 rise 9 times. Of course, this Q is a negative charge. Therefore, this is minus 5 into 10 rise minus 6 upon root 2, and this value is minus 9 into 10 rise 9 into 5 into 10 rise minus 6 by 1. So this is what I mean. So immediately you can see this number. This number is minus 45 by root 2 into 10 rise minus 3, and this is minus 45 into 10 minus 3. Since because of the negative sign, what will you say? VD greater than VA is important, and here also all the time the direction is important. If now I am writing W from A to D is equal to VD minus VA times small q, and where we will write substitute all the values, and here of course small q is given to be positive charge. Therefore this is post q into 10 rise minus 6 coulomb, and these are all in volts. So these are the numbers you have at V, at D, V at A, and at the charges. Therefore now you will do this simple calculation, and of course that you will do all your own. I don't want to do that. And now here you tell me this VD minus VA, as you can see VD greater than VA, VD minus VA is positive, is it not? So this is a positive, and this is a positive quantity that you get, and here is also a positive. Therefore this work will be positive here, is it not? So that is what I wanted to do. Now here from A to C, look at that geometry. Look at that geometry. D to C is also there. D to A, D to C. Remember, this is a square. Now your analysis is important, and your common sense thinking is important. It is a square. Therefore, BA is equal to BC. Is it not? Is it not? In C. Suppose if I am writing it WAD, right? WAD. Now, BC is equal to BA, therefore V at C is equal to V at A. A and C are at same potential. There is no potential difference between A and C points. Since VC is equal to VA, what does it mean? Implies shall I say VD minus VC is equal to VD minus VA. VD minus VA. Therefore here work from, yes, earlier we said work from A to D is same as work from C to D. Work from C to D. Now please, each and every line you look at carefully. A to D ಎಷ್ಟು work ಆಗುತ್ತೆ, C to D same work ಆಗುತ್ತೆ. Is it not? Whereas, but here in this example, what is that I have from D to C? From D to C ಕೊಟ್ಟಿದ್ದಾರೆ. So D to C and if it is a D to C, what happens? WA to D is equal to WC to D. Supposing if I do WD to C, then what does it imply? WD to C is negative of C to D. Is it not? WD to C. Suppose if it is higher to lower, then C to D becomes exactly opposite. Lower to higher it becomes exactly the reversal of the order. Therefore, you will get the negative sign. Therefore, in electrostatics, this can be another principle that you can remember, or you can observe and make it on your own. WD to C, because I have said WD to C. Therefore, in this, what is the answer that you get? WD to C is equal to minus of WA to D. So whatever work earlier you got, if you use with negative sign, that becomes work in displacing from D to C. Now tell me what is A to C. Look at this third part. Suppose if it is A to C, WA to C, we said A and C are at same potential. Potential difference is 0. Since potential difference is 0, VA minus VC is equal to 0 implies W is equal to 0. Which work we are talking about? Since it is VA minus VC is equal to 0, the work from A to C, or C to A is 0. This is what the concept of equipotential surface. Therefore, now A and C are on equipotential surface because they are with same potential. Is it not? Now remember, when I said A to C, if we displace the charge A to C directly or else A to D, D to C, then also work done is 0 because it is independent of the path, depends only on the position. Earlier also we have seen this is how your CET NEET examples are done. Now you see that when this question is given, options can be given in number of ways. Now W A to D, if it is W1 and D to C is W2, what different relations are possible between W1 and W2? Again we have said the same can be an answer. W D to C is negative of W A to D. Therefore A to D, W1, if it is positive work, D to C will be negative work and they are equal. Equal and opposite signs will be there. Supposing if this is negative, the other work W2 will be as positive. So the sign is changing but magnitude is same and hence net work done is 0 from A to C. How it is independent of path means A to C directly you make, then there is potential difference 0. A to D, D to C also work done is 0 because equal and opposite. Here work done by and there the work done on, the net work done when consider that positive and negative sign of equal magnitude will give 0 magnitude. So this is what the principle. Some charge is given, a fixed charge, another charge is displaced between two positions in calculating this work. Hope it is clear for you with proper understanding. Using the sign is very, very important. Writing the order is also important. Now let us see one more model of potential example. Yeah friends, look at this example. I said A and B are concentric shells. A and B are concentric shells with the radii small a and small b given to be 10 centimeter, 5 centimeter. The outer shell capital A radius 10 centimeter and the inner shell B radius is 5 centimeter. Now they are given charges. Outer shell with a charge of Q1 given to be 7 microcoulomb. B, the inner shell with a charge of 4 microcoulomb. This is what is the data. Now different possible questions are there. First one I pick one and the one I pick is if A and B are connected by, both A and B are concentric conducting shells, they are connected by a conducting wire. Now A and B are connected by a wire. What amount of charge will flow between A and B is the question. The question is, again 3 questions I will ask for. The first one is, number 1, when A and B are connected by a conducting wire, find number 1, I said common potential. Why here I called it common potential? We will have a discussion. It's a very, very important discussion. Find the common potential. Next one is find the quantity of charge. Find quantity of charge flowing between the shells. Flowing between shells. In fact, when you said between the shells, we have to make it a point whether the charge flows from A to B or B to A. That's also an important thing. So quantity of charge flowing between the shells, and also I will ask for the quantities, the final quantity of charge. Final quantity of charge on shell A or shell B. So these are the questions that I would like to do for this given data. But please see here, it's a very important principle that we discuss. It can be a board example for 5 marks, but afterwards, of course, any example we understand better way. Other examples for other competitive examinations you can think of, right? Now, Here you see the system says that A, outer shell with more charge, and B, the inner shell with lesser charge. Now the case. Last class when we have introduced the potential, we have made a star mark statement that the charge flow in electrostatics I have compared with the fluid flow in fluid mechanics and heat flow, you remember? Therefore, here you remember that statement. The flow of charges is always from higher potential to lower potential for positive charge, and the natural direction of flow is from lower potential to higher potential for negative charge. The potential difference is the key. Here you can see all these positive charges and all. Therefore, now here the flow of the charges is determined not by size. See that bigger size to smaller size, never it means. Also, it is never from more charge to less charge, never it is. In fact, what we should see for is higher potential to lower potential is our concept. Now, remember, first we have to compare that. Since we know that now, since V is equal to KQ by R, you remember this expression? V equal to KQ by R for shell on the surface. You remember this? We have derived this result for a conducting shell. Any point on the shell will be at same potential KQ by capital R, and it is the same inside the shell also was our result. Therefore, Vs is equal to KQ by R. What does it mean? It implies V proportional to Q by R. V proportional to Q by R. So when such examples are given with conducting shells and connected by a wire, the first point to be remembered is that now you need to look at this Q by R comparison. Therefore, now here Q by R for A, and take Q by R for B. What you will see? Q by R 7 by 10, and this is 4 by 5. Clearly, Q by R of A less than Q by R of B from data. From given data, yes, this is what is our outcome. It means that VB greater than VA. See, this is the beauty of this every time. When you say numerical example, physics is difficult. In fact, who is not ready with any of the fundamentals, definitely for them it's a very difficult thing. But the other way, if you are good at fundamental, it's a matter of 2 or 3 minutes, 5 marks in your board exam, right? VB greater than VA, hence charge flows from B shell to A shell is our. Supposing if this is what is the example in the board examination and this is what is your answer, I tell you, it speaks volumes about your understanding, volumes about your character as a student. An examiner is bound to make the paper 70 and 70, I'm telling you. This is not something you can find with many of the students. 1 in hundreds or 1 in thousands will find such beautiful explanation. First we have compared this Q by R, then we said the potential of B greater than that of A. And now here by principle it is always from higher potential to lower potential as the principle, charge flows from B to A. Now tell me, even in the case of fluid mechanics or other case of heat also, heat transfer is due to temperature difference from A to B, right? Until both acquire a common temperature. Supposing A is at a temperature of 50 degrees, B is at a temperature of 20 degrees. Now the flow is from A to B because of temperature difference until the temperature of both of them becomes one and the same. That is what we call common temperature. Here also the same. Now charge flows from B to A until both acquire A common potential, I say. There the temperature concept deciding the direction of the flow and the conditions. Here we have used the potential concept for the flow. Therefore, both acquire common potential. Both acquire common potential. Till that the flow will take place. This is what is our principle. Now in this principle what we learned that it is the flow from B to A. Remember here that is never decided by the charge alone, higher charge, lower charge, or bigger shape or smaller size or bigger size. It all depends upon that Q by R for this given geometry, which is a shell. Now tell me whether the charge flows or not. Our first day of electrostatics. First day of electrostatics we dealt with the properties of charges. There we said conservation of charge in any interaction, the physical, chemical, biological, whatnot, microscopic, macroscopic, all types of interactions, the charge of a system always remains constant. Always remains constant. Therefore now we will make use of conservation of charge. Now, common potential. If V is the common potential, let me write. If capital V is common potential, if V is the common potential, and then now you see, since it is the flow of charge from B to A, what happens? Q2 becomes Q2 dash and Q1 becomes Q1 dash. If Q1 and Q2 are the charges that we have shown, this is before connecting and this one is also before connecting by a wire. After connecting the wire, because of the flow of charges, Q1 and Q2 values have changed. The magnitudes have changed such that Q2 becomes Q2 dash, Q1 becomes Q1 dash. Is it right? Therefore now I am writing it as Q1 dash plus Q2 dash is equal to Q1 plus Q2, which is accordingly 7 plus 4, 11 microcoulomb. This is one thing. Now when we say common potential, what is the common potential? VB dash is equal to VA dash. Or first let me write VB dash is equal to K Q2 dash by what is that radius? Radius is going to be D, right? And what is that VA dash? That is equal to K Q1 dash by A. This is after connecting V1, VB dash and VA dash. Now we know that VB dash is equal to VA dash is equal to V. Both are same. And also look here, what is that VB dash by VA dash is equal to, yes, Q2 Q2 dash by, they are the same, right? When I take the ratio, VB dash by VA dash is Q2 dash by Q1 dash, or only one that I will write. What is that? K Q2 dash by V is equal to K Q1 dash by A, implies Q1 dash by Q2 dash is equal to, yes, Q1 dash by Q2 dash is equal to A by B. Q1 dash by Q2 dash is A by B. So this is one more result. First we had one result, what is that? Q1 dash plus Q2 dash is equal to 11. One expression we have. Now we have one more, that Q1 dash by Q2 dash is equal to A by B. Now what is that? You look at the symbols and understand that is A is the size of, the radius of capital A, and B is that of the shell B. Now here what is Q1 dash? Q1 dash. the charge on shell A and this is charge on shell B. Now what is that you observe here? Here you see Q dash proportional to R, the radius. Is it not? What does it mean? Whoever, when this charge you have to divide, charge division between two shells. Charge division between two shells whenever happen, they happen according to the result Q proportional to radius. More radius, more charge it will accept, lesser radius, lesser charge it will take, because it is always a distribution of the charge on the surface. Earlier Coulombic force examples we did, remember, when two shells are touched with each other, we have taken the case of identical shells. Same radius, same size, then the charge division is equal. Supposing 5 centimeter, right? If I have to give them 10 microcoulomb, then it will be 5 and 5 they will take because of equal size. When the sizes are unequal, please look at this example. When the two shells are of different sizes touched with each other, or a charge sharing between them, always in the ratio of radius. More size, more radius, you will accept more charge, and lesser size will always take lesser charge. So that's a very important point to be remembered. Now to discuss all these points, I have taken up this example, right? So now Q dash by, right? Now you see Q1 dash, Q2 dash. Therefore from this, what is Q1 dash? Q1 dash and the S2 bhaga barbeku, A parts. Q2 dash means B parts. What is the total parts? A plus B. Therefore what is Q1 dash? Total is 2, 11. Shall I write? Q1 dash is 11 microcoulombs is the total. Other आगे Q1 dash is बरबेकु A parts बरबेकु. This is A by A plus B. And similarly, what is that Q2 dash? Q2 dash is equal to 11 times B by A plus B. So this is how you have calculated the charges on the shells after they have been connected by a wire. Now the quantity of charge that flows. The second part is the quantity of charge. First we got the final one. The final quantity of charge on A or on B we have calculated. So this one is on A and this one is on B. So we got the final charges. After that, whatever difference is there, earlier we said it is from B to A, is it not different? Now in this example, Q2 dash will be less than Q2. Q2 dash Q2 gana kadime irutte, Q1 dash Q1 gana ಜಾಸ್ತಿ ಇರುತ್ತೆ ನೋಡಿ ಅಲ್ಲಿ, because it is from B to A. Therefore that difference, what is the difference now? Q2 dash minus Q2 Q2 minus Q2 dash, or else Q1 dash minus Q. So now let me show that. So what is the quantity of charge that is now flowing? What is the quantity of charge that is flowing? In this example, not all the examples. For this example, it is now nothing but Q2 minus Q2 dash, or else it is Q1 dash minus QB. A ಮೇಲೆ charge ಜಾಸ್ತಿ ಆಗಿದೆ. So that is what is the charge that is flowing, and finally the charges. Now we want that common potential. A common potential ಹೇಗೆ ಬರುತ್ತೆ ಈಗ ನೋಡೋಣ. Just one more last example that I want to do. ಅದು ಕೂಡ ಏನಿದೆ, look at this example. The same is the example where you can take the common potential, which is nothing but V common potential is equal to, I will write it as V A dash, which is equal to K, which is, I said, Q1 dash by A. Now we know the values of Q1 dash. A, K is of course 10.9, you can do it. The same is nothing but V is equal to VB dash also, which is nothing but K Q2 dash by B. So now evaluate either K Q1 dash by A or K Q2 dash by B, will get the same answer, and that is what is common potential. You do this example, afterwards what are the many other things that you take, also try to do. Because here in this example, step 1 was important, comparison of the Q by R, and after that the distribution of the charges. Once they got the common potential, how we divide the charge, and that charge division is also an important consequence principle that we can remember in our other examples. So these were some simple examples that I did on potential. We'll continue more examples in our next session. Till then, good day. Have a safe and secure stay at home. Good day, boys.